Hey everybody. Hey everybody. Let's take another test, shall we? This entire test is just going to be on DC circuits. So it's only covering Module 9, but everything in Module 9. First and foremost, you got to understand the definitions, the basic definitions of each and every term. A lot of people seem to forget what current actually is. It's just the movement of charged particles within a wire, and it's measured in amperes. Now, an ampere is simply a coulomb per second. Another way of putting this is current equals charge per time. An amp of current is 1 coulomb per second. Now, the entire purpose of resistance is just to slow the flow of current, slow things down. Because if current gets really fast, then wires get really hot, and that can be exceedingly dangerous. So you put resistance in there to try to slow things down. It resists the movement of these charged particles. Meanwhile, you've got voltage. This is from last test. Voltage is the amount of potential energy that charged particles feel per unit of charge that they have. So a volt is just a joule per coulomb. A lot of times I just imagine voltage as a drop. So what we're looking at is a change in voltage. Batteries provide voltage. Resistors have voltage dropped over them. Ohm's law is the magic law of this unit. Simply V equals IR. Now this works for the entire circuit. The grand total voltage is equal to the grand total current times the equivalent resistance. It can be applied to a single resistor, so the voltage drop on that resistor is equal to the current running through it times its own resistance. Or it can be applied to a simplified group. So if you've got a couple of resistors in series, such as on the right side of this circuit here, I can simplify that down to 6 ohms. Now I can use V equals IR over the simplified group of resistors to figure out how much current is going through this leg. 12 volts are being dropped over a total of 6 ohms, so that's 2 amps of current. That tells me that 2 amps of current are going down this way. Even when I bring it back to the original state that it was in, with a certain 4 ohm resistor and a certain 2 ohm resistor, I still know that 2 amps of current are going through this entire leg this way. And that can help me find the individual voltage drops by multiplying 2 amps times my individual resistances. A very important rule to keep in mind at all times as you're going through circuit analysis is Kirchhoff's voltage rule. That's saying that throughout the course of one path around the circuit, the total voltage gained is the total voltage dropped. So if you have a 12-volt battery, do not slap 12 volts on a single resistor unless that's the only resistor you encounter in a path. If you can chart out a path and you hit 2 or 3 or 4 or more before you get back to the battery, none of them will have the full battery's voltage on it. But they will add up to the total. The junction rule is equally important. You can't just magic electrons into or out of existence. The total flow into one junction of current equals the total flow out. That's incredibly important for circuit analysis if you know the total current from your battery and the current down one branch of a parallel split. You can find the current down the other branch using this rule. This is something that you don't necessarily have to memorize, just kind of logic your way through it. The current has to be the same for each resistor in series because there's nowhere else for that current to go. Current is the flow of charge over time. The same charges that go through one resistor go through the next one if those resistors are in series with each other. You don't add these currents up, you don't subtract them away, it's just the same. Now, voltage drop, however, is going to have to add up to the total across every little bit in series. Because for each path, the voltage gained is the voltage dropped. In parallel, the voltage drop is the same across the resistors in parallel with each other. That's because you can go down a path of one resistor or the other, but either way you go, you have to drop the same amount of voltage before continuing down the circuit. Now the current does add to the total. That's because current is the flow of charge over time. And if there's a branch in the circuit, Some of the electrons will go one way, and some will go the other. Make sure that you've got the equivalent resistance rules down pat. The grand total resistance is the sum of each individual resistor if they're in series, and if they're in parallel, you have to use that reciprocal rule. Don't forget, at the very end, you need to flip it. It's not enough to just add 1 over R1 plus 1 over R2 plus 1 over R3 and be done. That will equal 1 over your equivalent resistance. Instead, make sure you flip that at the end to get the actual equivalent resistance. A lot of times when you're doing circuit analysis, if you don't know where to start, the best place to start is to find the equivalent resistance. What is that grand total? You're going to have to go bit by bit, find areas where resistors are perfectly in series with each other and add those up. Find areas where resistors are perfectly in parallel with each other, use the reciprocal rule on those, and just slowly break it down little bit by little bit. You can redraw the circuit each time, replacing the resistors that you've broken down with just one single resistor with your new total value there. Once you've got that equivalent resistance, use V equals IR to find the total current. You know the total battery's voltage, you know the total resistance, you can find the total current. After that, it varies circuit by circuit. One thing you can always use is if there's a resistor directly after the battery or directly before the battery, the total current coming out of the battery has to go through that resistor. Otherwise, start drawing little loops for yourself and think about how your voltage is adding up across these resistors that you encounter on a single loop. It takes some practice, but if you remember those rules, V equals IR, the current rule, and the voltage rule, then you can do it. Don't forget as well my little waterfall analogy. It kind of helps me to remember what exactly is the same and what's added in terms of current and voltage. Remember that voltage drop is like a drop in potential energy. So that's here. Over a waterfall, that's like my resistor. All the current drops voltage, continues down the path, and then gets pumped up the exact same voltage. When you have a series circuit, all the current goes through every resistor. I'm not adding water molecules from this drop, which I'll call change in voltage 1, to this drop. Every single little molecule of water that goes over the first waterfall then goes over the second waterfall. But their voltage drops are not the same. And that's in series. In parallel, the current splits up. Some of it goes down path 1, some of it goes down path 2, some of it goes down path 3. But no matter what, the change in voltage is the same. And then the current always comes back together before getting pumped back up. And a lot of times you're going to face resistors that are arranged somewhat in series and somewhat in parallel. On one branch, maybe you have one resistor, and you drop the entire voltage over that. On another branch, maybe you've got a series of steps, and you've got a bunch of little voltage drops as you go. In these cases, break it down little bit by little bit, making it simpler as you go. Now you're also going to have to know a little bit about the power of a circuit. Power is just current times voltage. Power is measured in watts, current in amperes, and voltage in volts. The equation works well for the entire circuit, so the grand total power of the battery equals the current the battery is pumping out times its voltage, and the power dissipated in a single resistor is just the current traveling through that resistor times the voltage that is dropped over that resistor. Make sure you understand the differences between ammeters and voltmeters. Ammeters measure current, and as a result, they need to experience the same current as whatever resistor you're trying to measure. This means you must wire it in series, because objects in parallel don't necessarily have the same current, but objects in series do. Now, I also want my ammeter to mess with my circuit as little as possible, so it has to have very low resistance. If it had high resistance, the current would be much, much, much lower than it typically is, and I'd get a bad reading. But with low resistance, I'm essentially just putting another wire into my circuit, and that won't mess things up very much. Now a voltmeter, on the other hand, measures voltage, and like all electrical components, it only experiences the same voltage as a resistor if it's placed in parallel with it. So put your voltmeter in parallel. Now I also want it to mess with my original circuit as little as possible. Since it's in parallel, I only want it to draw a tiny little bit of current, not much at all, because otherwise my resistor would have less current running through it, and that changes things. So as a result, my voltmeter has to have very high resistance. Resistivity is a property of a wire that determines how much resistance it'll have. Think of it as walking down a long hallway. The longer the hallway gets, the more opportunities you have to bump into somebody, and that'll slow you down. The slow of the flow of current is resistance. Also, in a wider hallway, you're less likely to hit as many people as in a narrow hallway. With a narrow hallway, you're a lot more likely to get jammed up in traffic. So once you know the resistivity of the material, just multiply it by the length, divide it by the cross-sectional area, and don't forget, this is something that you'll probably need to know. The cross-sectional area of a wire is pi r squared, because it's a circle. Now, resistivity also changes with temperature. So we start at a base level of 20 degrees Celsius, that's about room temperature. Delta T is going to be the change from 20 degrees. So if my wire is at 80 degrees, then delta T is going to be 60 degrees. And that's what actually goes in the equation. Alpha is what's known as the temperature coefficient, and it varies material to material. Basically, the change in temperature affects some materials more than others. If you have a high alpha value, a little change in temperature is going to add a lot of resistivity. If you have a low alpha value, the change in temperature doesn't affect things as much. Regardless, find your starting resistivity at 20 degrees Celsius, plug it through this little bit, and find your new resistivity. Once you have that, plug that in here for your resistivity value, and find your new resistance. We've also talked a bunch about capacitance. Here, you'll use the equation Q equals CV. This is basically the magic equation of capacitance. Q is the charge on each plate, that's measured in coulombs. C is the capacitance measured in farads. Make sure you've got this straight, because it's really easy when you see a C to assume that it's charge in coulombs. It is not. Now the energy stored in a capacitor is just 1/2 times the charge times the voltage. When a capacitor is initially hooked up to a battery, it acts like a wire, because it has no charge built up on it, it has no voltage on it. As charges approach down the wire, like charges repel on the other side of the capacitor, until they build up enough voltage that charge stops flowing, at which point the capacitor acts as a break in the wire, and current stops. A fully charged capacitor can then be put in a new circuit and be allowed to discharge. We'll talk about that in just a second. If you align capacitors in series, they have the same magnitude charge on each plate. That tells me the total charge that the battery spits out is equal to the charge on capacitor 1, it's equal to the charge on capacitor 2, it's equal to the charge on capacitor 3. This is because the final plate of capacitor 1 and the first plate of capacitor 2 are simply conductors that have been polarized by the presence of this charge. So they build up the same charge to reach equilibrium in the system. Then it happens again here, it happens again here. Now, just like all electrical components in series, voltage adds to the total. Now, the equivalent capacitance in series looks a lot like the equivalent resistance in parallel, so make sure you don't mix those up. When you arrange capacitors in parallel, now the charge doesn't have to be the same. This is because the battery is directly feeding each capacitor individually. So there's no reason for the charge buildup to be the same. However, just like all electrical components in parallel, the voltage that's built up in between them is the same as the voltage in the battery. As a result, you get an equation like this for capacitors in parallel. This looks a lot like resistors in series, so be careful not to mix them up. We closed out the unit talking about RC circuits. you'll use a different equation whether the capacitor is building up charge, or whether the capacitor is releasing charge or discharging. In both of these equations, Vc is the voltage on the capacitor at any given time, and this value changes as time passes. That epsilon there, Greek letter epsilon, is the battery voltage, known as the EMF. T is the amount of time that the capacitor has been charging, and tau is the time constant. Take your resistance in ohms, multiply it by your capacitance in farads, and that's your tau value. Make sure you go back to base units, because a lot of times you'll be dealing with stuff like kiloohms and microfarads, which reminds me, a common issue on every single test, and I expect it will be again this time, know your unit prefixes. I'm going to go ahead and add a few little lines of flare here. I'm actually going to make this a multicolored thing because I really need to get your attention here. All your metric prefixes are super important, and if you don't know whether micro or milli is times 10 to the negative third, review that. Here, I'm going to put some little loop-de-loops to make it even more, look at me. Some people like animals. Maybe I'll put a little cow face on here. To really encourage you to look in this direction, make sure you know those metric prefixes very, very well. That's it. Goodbye.